Hello everyone, welcome to the Jayhawk High-Powered Rocketry's Argonia 2026 video. My name is Benjamin Smith. I'm a junior studying aerospace engineering. In this video, we'll be talking about the design, manufacturing, structural, propulsion, avionics, and the recovery of our rocket. Welcome to Jayhawk Engineering.
Hello, my name is Connor Mispegel. I'm a junior here at KU studying aerospace engineering, and I'm this year's chief engineer. We started our design process by taking a look at last year's design and the new rule sets. Through this review, we found that the most effective way of increasing our points were minimizing our diameter and increasing our altitude. We confirmed this using simulations like RAS Aero and Open Rocket. And through the simulations, we also found the velocity and the max altitude.
Hey, I'm Jaron. I'm a third-year aerospace student here at the University of Kansas, and I am the propulsion sub-team lead. So our main responsibilities are motor selection and motor performance. For the motor selection, we went through a bunch of different configurations for our rocket, and we wanted to test how we could get the best apogee with the best amount of impulse for our rocket. We went through multiple different iterations, and we found the best that suited our rocket and our needs. And for the motor separation, we ran it through different simulations, and we talked to industry professionals to find out what we needed to do. And to speak a little bit more about this, we have Yugansh.
Hey guys, I'm Yugansh, and I'm a third-year aerospace engineer at the University of Kansas. To find our best separation delay for our rocket design, we went with RAS Aero and we used Excel. What we did was we ran multiple iterative cases for other rocket designs, and we found the best separation delay. We did 1 second separation each time, recorded the data we found with a couple of the motors we used to find the best combination we could use in our case. And to have the highest separation of delay while still giving us the highest apogee and still being under the impulse set by the Argonia Cup. We ran 3 cases with 3 different types of motors while still having our same motor for our booster. And by doing that, we found out that while even 1 second delay in one motor case can give you a lot of amount of apogee difference. The highest we recorded was around 3,000 feet. And doing multiple iterative cases, we found that our best separation delay was set, and we recorded that time and we used that. Now to talk more about motor integration with our substructure, I'll hand it over to our structures team.
Hi, my name is Jaden Webster, and I'm the structures lead, and I'm a junior here at University of Kansas.
I'm Corbin Zabrowski. I'm the structures deputy, and I'm also a freshman here at the University of Kansas.
Well, we mostly focused on the structure of the rocket, and so we built the airframe out of a fiberglass composite. And at all separation points, we used fiberglass couplers that we built here to maintain structural stability.
And those fiberglass couplers are made out of a braided mesh, and we use a hands-wet method to construct those.
Another thing we focused a lot on was fin flutter, and so we used large epoxy fillets to help reduce the chances of fin flutter from occurring. And overall, I would say we've built quite an impressive rocket this year, and we're excited. Another thing we did was we worked quite a bit with the electronics team to get the right volume for the avionics package.
So now we'll hand it over to the avionics team.
Hello, my name is Connor Fortin. I'm a junior studying aerospace engineering here at KU, and I'm currently the sub-team lead for our electronics team. On our rocket, we have 3 featherweight Blue Raven flight computers, 2 featherweight GPS trackers, and 1 Altus Metrum telemetrum. flight computer, and tracker. These electronics are all off-the-shelf components, and they are all run on their separate power system. Each individual electronic component has its own battery and own power system, so if any one system fails, there is redundancy to ensure that the rocket maintains control. The control logic of the rocket determines the heading and the flight path angle of the rocket and determines if it is safe to ignite the motor by determining if it is within the safe bounds of class.
Hi, I'm Sam Brower and I'm a junior in aerospace.
Hi, I'm Prabhakaran. I'm also a junior in aerospace.
We were the co-leads for the Argonia payload team, and we designed and built the payload section for electronics and golf balls. We had a decent amount of constraints in terms of size and the capacity.
So we worked in tandem with the electronics team, and we basically custom made and designed a 3D printed sled that houses all of our avionics systems and batteries. Our design intent mainly centered around saving weight and being structurally rigid. We made multiple iterations, and as I said, we 3D printed our final product. The structure is housed in a rocket using two threaded rods that go between two bulkheads.
The golf balls were a little more simple, as all we did was research some soft elastic materials in order to better hold the golf balls securely during the launch, and that is then housed in the sustainer section. And everything should go to plan.
Safely recovering both the booster stage and sustainer stage were crucial for our mission to be successful. Hence, we took extra care when selecting and packaging our parachutes. Since the booster stage won't be nearly as heavy as our sustainer stage, we opted for a 4-foot parachute that will deploy shortly after the booster's apogee. Since the sustainer stage would be heavier and fly higher than the booster, it needs a more robust recovery system. Hence, we employed a dual deployment system with a drogue and main parachute. The drogue chute of 2 feet deploys at apogee, sensed by the redundant flight computers, and the main parachute of 5 feet deploys at 1,000 feet in altitude, also sensed by our flight computers. Our target landing velocity is around 15 feet per second, which is well under the 35 feet per second requirement set by the Argonia Cup rules to ensure a safe recovery.
Hello again. Thank you for watching our team video. We hope you guys learned a lot about our rocket, and we'll see you guys at the competition.